Hi, this is a linear algebra, section 2.2. We'll get started. Number one, so basically we're trying to figure out the determinant for original matrix A and its transposed matrix of A. So don't worry about B for now. I just wrote this as just so that just for people who may not fully remember what transposon is. But nonetheless, so we're given this matrix, and finding del A should be pretty straightforward by now. So I didn't even bother. But again, it's gonna be just A times D minus B times C, right? So just follow through, and then that's gonna be 11, right? So ignore this, negative 11, right? So transposon, for people who may have forgotten, just look at this as a brief reference, right? So I just said let B be another matrix with A11, A12, A21, A22 as the entries. And as we know, the first number on those two digits is the first one is representing the number of row, and then the second one represents the number of columns. So so first entry here, row 1, column 1, row 1, column 2, row 2, column 1, and so forth, right? So with transposons, all we're doing is making sure row and the column are switched, which is why A11 and A22, they stay the same, because even if you flip them, it's going to be the same thing. If you have 1 and 1, flip those digits to get around, and then you still have 1, 1. Same goes with these. However, for these one, if I flip this, it's going to be 2, 1, where 2 is the row and 1 is the column, right? So this got to go here, as shown here, right? So anyway, so yeah, do a brief review if you're not sure, but this is pretty straightforward as far as I'm concerned. So we're gonna keep pushing, right? So number 2, same idea, right? If you don't fully remember transposing, just do this too, just in case. But for most of us, it's not really a problem. Let's try now doing number 3. Okay, so on to question 3. So again, nothing new, or it shouldn't be anyway. But yeah, it's just finding a determinant when you have matrix a matrix size about 3 by 3. So again, you're just doing you choose a row or a column or whatever, or whichever you prefer, and we'll talk about which one you should be choosing. But nonetheless, let's say I chose this one as the solution book implies, 2, 1, 5. So if that's the case, it's 2. So so this is the row 1, column 1, right? So we ignore column 1 and row 1. Then you have this 4 entries that are left over. So essentially what we do is 2 times, and remember the sign chart, or what it was called, right? Positive, negative, positive, negative, positive, negative. Remember that, right? Make sure you draw the chart if that's how you're going about with this. Because let's say this is on the positive position, right? So because of that, it's going to be 2 times 1. Right? Where 1 just represents a positive number. But if it was this number, for example, 1, right? You guys can see, yeah, I'm actually just going to draw this just so that you guys know what I'm talking about. So I'm talking about this chart. You can sort of see it, but so first and so forth, right? And again, this applies to any dimensions. I mean, chances are 3 or maybe 4 is as much as you go. But let's say let's say I just changed the size to, let's say 5 times 2, for example, right? Because of the space, right? So if that was the case, then really all I have to do is just, it's gonna be just positive, negative, positive, negative, positive, negative, positive, negative, positive, negative. That's all I would do, right? So make sure you have this chart handy, or just memorize it in your head, right? But to understand, as long as you understand, it shouldn't be too much of an issue. Our professor said this once. It was a bit of a cliche, but I thought it was kind of cool. It's like, look once and learn and understand forever. So, anyways, but yeah. So that's how you're supposed to be doing. I don't like doing I don't like to find, but okay. Let me rephrase that. What I mean to say is, if I just start to find the determinants from this, then I have to 2 times this determinant, 1 times these 2 determinants, because remember, this is row 2, column 1, right? So I have to ignore row 2, and I have to ignore column 1, which means the only thing left is, see, -1, 3, and -3, 6, right? I'm not sure if my hands did the justice. Okay, well, whatever. Yeah, but you understand the idea. Review back if you must, but to earlier section. But this I shouldn't be talking too much about this. So anywho, so what I did was I got rid of 2s and 5 using this leading coefficient on the second row. Got myself 2 zeros using these, and then bullseye. Now I can just ignore 0, 0 because 0 times anything is 0. So I just need to find the determinant 1, and then -5, -5, -13, 14. So this is what I wrote. I still wrote down to 0 anyway, just to show you guys. But ultimately, as you see in the other question here, this time I ignored it because it's just worth getting redundant, right? So yeah, just browse through, right? So finding determinant of 2 by 2, we should be pretty comfortable. That is this. Just make sure you don't mess with the signs, right? Right. For example, here, right? So based on the star chart, sign chart we were talking about, right? So that could make a difference, right? So that's that, right? Oh yeah. Oh, crap. Okay, I wanted to fit everything in here, but okay. So freeze this. Make sure you get to this point. Okay. The reason why I'm raising is because I have to compare that with the delt of an A. I have to find the delt A transpose, right? So I'm still gonna use this, right? Hopefully that would, yeah, I could do that. So then A T is gonna equal to 0. Okay, so this is my strategy. Because it's row 1, column 1, row 2, column 2, row 2, column 3. So they're not gonna change regardless of what you do transpose on. So then I look at this one, so it's gonna be -1 and 1. Because these two will change, right? This is 1, 2, and 2, 1. So just like what happened before, right? And then 5 and 0 will change. 0 and negative. Oh, nah. No. I forgot to switch it. -5 from here, right? I'm switching these two. And then what's left? These two. -13 and 4. So it's going to be 4, -13. But ultimately, you can see that it's going to be exactly the same thing, right? Because so instead of using this column, first column, I'm just going to use the first row this time, right? That's all I have to do, and the rest will be pretty simple, okay? So it's going to be 0 times anything 0, so I don't care. 1 is going to be 1. The sign is on the negative, right? Positive, negative, right? So that's going to be negative, and then delt of so get rid of this and get rid of that. You have this 2 left, so it's going to be -5, -5, -13, -14, and then 0 is whatever, times anything 0. And we've seen this before, right? So, we can just, so that's going to equal to -5 again, right? So that's all there is. Okay, I'll let you take a look at number 4. Same idea, just follow through while I work on this transposon counterpart. So transposon is going to be kind of silly, but 0, 2, 5. I mean, can't I just tell everyone that if you have a transposon and the regular matrix, it's going to be the same? See, I wish I could say that, but I don't have a definite proof. I suppose I could find one, but this is easier. So that's that. Then I'm just going to find the determinant now. A equals to 0 plus 0 plus -1. And I didn't put -1 because of the sign chart, right? It's just -1. Sign chart wise is positive, negative, positive, so it should be positive. Just so that you guys know. And then it's gonna be here is 6, 2, negative, yeah. 6, 2, negative, no. Yeah, no negative on 19. Okay, so if that's the case, so it looks a little different, but again, it's the same idea there, right? So it's gonna be okay, well, yeah, but yeah, exactly. So then what it's gonna be is -1. It's gonna be 6 times 3. I wrote this wrong? Oh, no, it's not. No, it's fine. Minus 19, 2. And yeah, you know that you see that's exactly the same, right? Even though this looks a little different, but it's the same idea when when you're just looking for determinant. So this is also going to give you 56. So that's all you need to know. We're going to move on to number 5. That's where 2.2 really begins. Okay, so we're going to question 5. I wanted to put as many questions as possible, but I just wanted to make sure we're 100% clear on the theorem before we continue to blitz our way through, so to speak. I think earlier in the comment, and I'm too lazy to edit this video out, I made a stupid comment by saying, well, like I can't really show you the proof where the matrix A and matrix A transposon will have the same determinant. That is false, so I do apologize. So, which is reflected here, right? Determinant A is always going to equal the determinant of the same A transposed, right? So, but we'll get to that later, right? I just want to, let's talk about the overall theorem first, and then once we're clear on this, we should be able to slam through the rest of the questions. So now, okay, so she should have made it clear, but you know, this is a chance for us to be 100% clear, so let's just bear with me here, okay? So single row or single column is multiplied by scalar k, then delt B equals delt A. So what does that mean, right? So this is really fancy way of saying, oh, no, what have I done? Sorry. Yeah. I was trying to test you if you guys were paying attention. K delt A. Okay, so all it's saying is basically if, like for example, number 5, this is a great example, right? So this looks like an identity matrix, right? 1, 1, 1, 1, but except it's not 1, there's negative 5. So this fits this specific condition beautifully, right? So single row, in this case, or single column, really doesn't matter. I could say single row or single column, right? Is multiplied by scalar k. So in this case, it will be negative 5, right? Because it should be 1, so it should be 1, 1, 1, 1, but this is negative 5. So let's just say k is negative 5, right? So if that's the case, then delt B equals to k delt A. Now some people might frown upon this because of this key word. Because it says scalar, right? So negative 5 is not scalar. Scalar, if you remember, there's scalar and vector, right? So scalar technically means just, you know, just regular distance. Remember Maria used to give us a lot of a difficult time trying to explain how there is no such thing as negative x, which actually makes sense. Because there's a difference between negative and minus. Yeah. So there. So some people might be confused by this, but this is the theory, right? So x, if I say x equal to negative 5, this really means 0 minus 5, right? Because if we're talking scalar or distance only, right? Like there's no such thing as negative number, right? It just means 5. It means a distance of 5 from 0, right? Towards left. Some people think this is a really, trivial, but you know, so I just wanted to make that a little more clear, right? So that's why. So technically speaking, we should make this scalar. But you know, but again, this is a reason. Like we're not trying to become a math major, and if you are, I do apologize. But for most of us, you know, we just want to make sure, like, know how this actually works. So that sounds ironic coming from a comp sci major. I know, but so think of it this way: if k has to be scalar, then negative 5 has to be 5, right? So then this makes sense, right? So the new delt will be 5. And delt of the original, which would have been 1 times 1 times 1 times 1, right? So this would have been 5 delt A, right? But it didn't, but we could say scalar k minus, right? And then this will be equally minus, right? So we could say that. So ultimately speaking, I don't think it really matters as long as we understand that okay, like if we times a row or column by some number, right? You know, some number, that then it's gonna be, you know, just so that's just gonna be, you know, so if in this case negative 5, right? So I'm just gonna put say k is 5 negative if you want. So the point is it'll be negative 5 times the determinant a, right? Before this transformation. So before then it will be 1 times 1 times negative 5 times 1. Sorry, 1 times 1 times 1 times 1, right? So that would have been the case. So that's what it's basically trying to say. So because of that, for that number 5 question particularly, it will be negative 5 and del A, and the original del A will be 1, 1, 1, 1. So in this case, we should say this is the B, because there's a transformation, right? But again, just trying to show you what the rules really say, right? So that's the idea. Okay, so that's number 1. Oh, and for this case, we didn't really have to use this rule, but it's nice that we appreciate that, because later on in the question, we're gonna actually use these to make sure we're not messing up with signs or, and so forth, right? So here, we don't really have to, because if you remember, right, remember the upper triangle and the lower triangle and those things we talked about in, I don't know, 2.1, I believe, right? But, yeah, so basically, if you manage to have, this is the diagonal center, right? 1, 1, negative 5 here. So if all entries on top of the diagonal line is 0, in this case, both of them, right? So, so we call it diagonal triangle, but nonetheless, right? So as long as one of the triangle has all entries of zeros, right? So this imaginarily, right? That triangle, or this triangle, right? So if that's the case, then determinant is just going to be just multiplying all the entries that goes through this diagonal line, right? So 1 times negative 5 times 1 is negative 5. So it gives us the same answer, right? But nonetheless, we should be familiar with this rule, right? So because we can't always make this nice triangle. Anyways, so the number 2, the condition is 2 rows or 2 columns, not both, right? They're separate, right? 2 rows or 2 columns are switched. So you can't do row switch with column. I mean, oh wait, I think you can, but that requires multi-dimensional transformation. That may not be cool. But anyway, in here. So that's what I'm saying. So basically, like, when we're doing eliminations, right? Sometimes we have to switch the second row to third row for whatever reasons. Often we have to do that to make sure our matrix looks like identity matrix or whatever, right? So in situations like that, every time when you make any switch, whether it's row to row, like second row to third row, or column 2 to column 3, as in, for example, right? Every time when you do that, your determinant is going to have a negative sign. Now, some people might be puzzled by this. Wait, what do you mean, like, switching 2 columns? We only switch rows, right? Well, remember that, and I should have made that a little more clear, but in question 1 and 2, the whole point of doing those exercises to give us some idea that determinant A is going to equal to determinant A transposon. So what happens when we have an A transposon, right? Rows and columns are switched, right? So essentially, if rows and columns are switched, but the determinant stays the same, then it really doesn't matter whether we manipulate by row or by column, because this is like by row and this is by column, right? Think about it. So it's kind of like, so determinant A, like the row, we're going by the rows like this, right? Here it's gonna go like this, but they're the same. So that's why we say switch the 2 rows or switch the 2 columns. So, but you get the idea. Number 3. This is the regular. So I mean, there's a fancy way to say it, but I thought I would just cut to the chase. Any regular elimination will not affect the determinant, right? Not just rows by columns. Yeah, we just talked about that, right? So for any regular elimination, maybe we don't need this comment because we made that abundantly clear. So in regular, you're gonna have delt B equals to delt A. So basically that's a fancy way of saying determinant will not change if you just do regular elimination. So let's say second row plus 3. So for example, if I had like R3 plus negative 5 R2 gives me the new R2, for example, right? So for that, it's a regular elimination that we've been going through, so determinant will not change. And you should know that, right? Because remember, whenever we have 3 by 3 size matrix or greater, right? What's the one thing we always do? We try to make as many zeros as possible in same column or row, right? Why, if we, let me rephrase that. The reason why we do that, because as long as we're doing regular eliminations like this, right? Determinant will not change. So that's why. If the determinant does change, yeah, we don't want to touch the matrix. We want to just go to this determinant equation right away. But, so anyways, those are the theorems that should be drilled into your head. And number 5, this is the answer, right? We will push on to number 6, but have this handy, write it down or memorize, right? Because not all of us can see once and understand forever, like Maria. So, moving on to question 6. Okay, so blitzing from 6 to 8. So, take a look at 6 and see what I did. So, yeah, so I mean, technically you could just ignore it because we already see a diagonal here and the triangle's there. So all we can do is do 1 times 1 times 1, that would give us 1. Or if you would try to implement what we learned with those determinant rules, right? So if that's the case, then I could also say, or this is the same, I could get the first row as shown here, times it by 5 to get rid of the leading coefficients, and I'll have that. So remember, whenever we do elimination, it doesn't affect delta A, determinant A, right? According to the number 3 from the theorem we talked about, right? So because of that, it's going to be 1, right? Because it's 1, 1, 1, right? Same thing. So you don't have to really do this for questions like this, but later we will. Let's look at number 7. So number 7 looks like this. So if you stare at it for a bit, you'll realize that, hey, that looks really, really similar to the identity matrix. And the only way that, and I can just easily just switch the second row and the third row to just make it look like the identity matrix. More importantly, I have triangles. So here we can't use, oh, by the way, that's a good point. We can't use triangle, we don't have upper or lower triangle. So because of that, we can't just times them up like we used to, see? So some people might say, well, 1 times 0 times 0 times 1, can't I do that? Here's the thing, your triangles, upper triangle and your lower triangle, right? They're not all zeros. The entries, there's one entry here, and there's another entry that's 1, right? So can't use upper or lower triangle. So in that case, we have to rearrange it. Now we have upper triangle and lower triangle. But this is where people might make a mistake. It's like, oh, that's it, right? Then it's good to go, right? You can't do that though, right? Because we switched it, right? Row 2, row 3. So I shouldn't put a equal mark here. I keep doing that. I haven't lost marks for that, but technically that's not quite the case, right? So, because, it's not the same matrix. But anyways, so we switched it, and if we switch the rows, right, or columns, here we only switch the rows, so we don't, but nonetheless, it's going to be number 2 will be effective in the theorem, right? And based on that, delta will be negative. So again, just look back to my earlier, look back to your note, or look back to the video just before question, or just when I was doing question 5. There has a list of theorem, right? We just looked into that. So now look at it again. But because of that, I'm just still gonna do 1 times 1 times 1 times 1. But my determinant will be negative, right? So I'm gonna put negative 1 here so that it becomes negative 1. Number 8. This is a similar idea as this, sorta. But I have this, right? So as you can see, this looks like a linear matrix, all beautiful and all, but this one's off, right? But still, if you are rushed for time, and actually whether you're rushed or not, it doesn't really matter. It really doesn't matter because we have upper triangle. We also have lower triangle. So if that's, okay, this is getting really ugly, but yeah, okay. So because of that, we can just simply do 1 times, so I could just go right on the get-go and just say 1, negative 3, 1, and 1. And that would give me negative 3, right? Another way you could do is we could take this one out, because according to rule number 1, which I haven't wrote down, but according to rule number 1, what did you do? Any row or column times the scalar k will mean k times the determinant, right? So that's what I did. I took the negative 1 over 3 determinant, and then since I took it out of here, it's going to be like that. So 1 times 1 times 1 times 1 times negative 1 over 3. Give me, so either way you do, it's going to be the same. I'm just introducing right now so that when I do a little bit hard ones like 9, 10, 11, you guys can still, keep up with your feet, so to speak. So, anywho, that is that. We're going to jump into question 9. Okay, so this is from question 9. I'm just trying to get the foundation really solid so that you guys don't get lost in 2.3. So, bear with me here. But nonetheless, okay, so for number 9, this is what I did, right? So I had this original one. Just wanted to clarify, and you guys will find this evident too when you look at the solution manual, if you have any. Good news about this is unless they change the questions, you wouldn't even need solution manual. But nonetheless, so what you have, so from here, all right. So when we rewrite it, we're looking for determinant A, right? So that is this, right? But notice the slight difference here, right? I know in our classes we use circles, but like this one. No, just because of my nostalgia with Matrix movie, but nonetheless, right? So this and that are not the same. This is going to be either curved parentheses or it's going to be those like square thing that we are used to. This one will be flat line because that flat line represents that this is going to be a number. This is not a matrix anymore, right? Which makes sense because we're looking for determinant of it, right? So. Just be clear on these formalities. If you're not, Maria will cook you alive. So, oh, interesting. Anyway, no, okay. I was thinking on something else. Gotta stop watching Hannibal Lecter. Anyways, so that's that. So, this was my solution. So I noticed that this nice 3, negative 6, and 9. That really stood out. I wanted to take a factor out by 3. So remember the first row, right? First row, times k. Means, so remember this is 1, right? I'll just write here so that you can look back what I mean, right? So took the 3 out because it's going to be, if it's k times a row, then it's going to be k times determinant of its matrix, right? So 3 times the determinant of the matrix. So go back to number 1, but that's what I did. After that, all I did was, I'm just going to go through the elimination. I wanted to get rid of the second, and all I have to do is get rid of the second one, right? So I just did row 1 times 2 plus row 2 equals 2 new row. So basic elimination. Now, this is number 3, right? But, this is number 3, but is the determinant effective? No, because elimination does not change the determinant. So, move on. And then what I did was basically I just decided to find the determinant from here, and this should be easy, right? I'm going to use the first column because it's got double zeros, so it's going to be 1 times 3, 4, 1, 5, right? Rest will be just times by 0, so who cares? Find determinant, I got 33. Now your solution does something a little different, and I'll let you decide what strategy you would prefer. I prefer this because it's straight away. But the solution manual shows you something different. So let's look at it. So I'm not going to start from the scratch. Basically, we both went up to this bay, right? So I'm just going to start from here, right? Now, what they did was they actually switched the second and the third row. See? So switched is like that. And remember that was number 2, right? What does that number 2 says? If the columns or the rows are switched, then the determinant is going to be now negative, right? So because of that, there's where the negative 1 comes from, right? So keep going. So what are they doing now? So now they're going through elimination to get rid of that leading coefficient of 3. See what they're planning to do here, right? Hey, why are they trying to make all these zeros? Because they want to create the lower triangle, right? So if they have the lower triangle, then all you have to do is just times this, times this, times this, right? So we're not quite there yet though, right? Because it's not. Because, oh, actually, you know what? No, okay, solution method is not being very elegant. Because if I did the elimination to get this, right? I mean, technically speaking, I have the lower triangle here, right? So if that's the case, so I understand why they did. I understand that this makes sense, like I'll get to that later. But if it's 0 and 0 is 0, right? Lower triangle, right? That means, hey, it's lower triangle. Just times 1 times 1 times negative 11 times negative 3 in front, right? So that should have worked. They took the negative 11 out though. I'm not sure why, but it's not wrong though. So all they did was they just said, well, so this is just like if I had 0, 0, 0, 1 for the third row, right? So that's like I did k times the third row, which is k where the k is gonna be negative 11, right? So it's gonna be So they just factor out the negative 11, just like what we did with number 3, and so this will be 1. So you have a right triangle down there. Lower triangle here, 1 times 1 times 1 times negative 11 times negative 1 times negative 3 is going to equal to 33. So it will give you the same answer, but I prefer mine better because it's similar to what we've been doing so far, and the solution is much more elegant, right? As Austin would say, and Austin and Philip might say it's a much more efficient solution. But anyways. But yeah, so this I think is unnecessary, but you know, it's not wrong, right? It's like 2 times, anyways, no, I'm not going to picture with stupid other examples of mine. So, anyways, that covers 9, and hopefully next, for the next part, I will be able to finish it without making it too lengthy. Alright, so that's number 10 and 11. So again, I think I'm mostly using cofactor because like that's something we're all so used to. So I mean, it's pretty straightforward, just follow through. Here I didn't even bother touching anything because hey, the second row is 0, 0, negative 2. That's awesome, 2 zeros. So you know, 0, 0, negative 2. Just be careful, don't forget the stars, the sign chart, right? Plus negative, plus negative, plus negative, right? So that's gonna be negative, right? So that's gonna be about, you got 30. 11, you know, looks intimidating, but, you know, pretty simple nonetheless because there's a large zero. There's 2 zeros already. I can use the elimination process to get rid of this one just by doing 2 times the second row, negative 2 times second row, add first row becomes first row. So I just did that. 3 zeros, perfect. I only have this one to deal with. So it's going to be 1 and sign chart again, right? Positive, then that's going to be negative. So that's going to be, you know, so follow through. And then I have this, I'm not quite done. I have to go first. I have to find the determinant of that as well. So, you know, I did the elimination, 2 zeros, you know, as she would say, sing the same song, right? So, yeah, so that's done. I think, you know, just for long-term purposes, we should also be comfortable making the upper and lower triangles or diagonal triangles, but ultimately one of them will do, right? Suffice, right? So I'm gonna try to do that on the next board. Okay, so so I recommend that you actually try to solve the question on your own rather than just blindly following through the solution manual. Simply because following through a solution makes, you know, relatively easy sense. You're just checking, was there an algebraic mistake here? Nope, keep going, right? So I encourage you to try to do this on your own, even if it doesn't quite, you know, even if you feel like, oh, I got this, it's pretty common sense, right? But nonetheless. So again, we did that. So we have this, we're doing the same question in 11. This is not a new question. I'm just trying to use that upper-lower triangle method to get this work. Someday, sorry, I know some people are making a lot of Illuminati jokes on this, so it's like, what? I still don't get it. Like, why Illuminati? It's just that I happen to know more about what the Illuminatis are. It's a scientific code. Like, who came up with this idea that they control the world? Sorry, geopolitical nightmare. So, that's kind of. But anyways, I'm getting distracted here. So anyways, so you have that. So basically all we did is we just switched the second and the first row. Now, let me tell you, so that leads to negative. Now, the important thing here isn't really about, oh, do I follow this? Because you can do that in solution manual too, right? What are they thinking? How are they making that, in this case, lower triangle? But the same concept applies, so even if you're doing upper triangle or whatever. The reason why, basically now we have to understand ourselves why they did this, right? Why did they switch it, right? Why did they just eliminate right on the get-go, right? It's because I want the leading if this is my leading coefficient, right, I want that. That's why I want to use this to get rid of that one, right, so that this becomes 0. I want the first leading coefficient on the first column, right? I want that to be at the very top, right? Like identity matrix, right? So it's like first leading coefficient is going to be on the top, then down, like that, right? So I want to mimic that, right? So I want this, which is the leading coefficient probably, right? For the first row eventually, right? I want that to be up there. 2 is in the way, right? Everything's 0, so he's the only leading coefficient. I want that, just like the identity matrix. That's why I switched it, right? And then I can use that elimination to get rid of that. See? Now we're a step a little closer. Here is all 0. So now my next goal is make this 0, make this 0, and then once these triangle is all 0. You guys see? Okay, how about we do this? So this is a diagonal line, right? Once I get everything below this pen to be 0, the mission I'm saying the same thing and Marie is saying. The mission accomplished. That totally sounds like what. That's a red alert to line. Or okay, I'm getting really distracted because I'm getting tired. But nonetheless, okay. So that's the plan though, right? I want this to be so these 3 are zeros. Now this 2, 1, and 2 right here, I want to make the 0. So how do I do that? So what we can do is, well, here, there's 1 and 2. This, I can use the leading coefficient here to get rid of that. So this is what she did. This is what the solution manual did, right? So use the 4th row to get rid of the leading coefficient in the 3rd row. So this is what I did. Or, I actually think about it, it could have been a lot faster. Just get the 2nd row, because he's going to be my leading coefficient anyway, because I want both of them gone anyway, right? I could have just used this to get rid of all that. They're doing it slowly one at a time, but nonetheless, you get the idea, right? So, so use that to get rid of that. So this is the only thing that I need to get rid of. I can use this leading coefficient to get rid of that. So it becomes 0 like that. So good. Almost done. This 1 is in my way. So how do I get rid of that 1? Well, see, I can't really get rid of 1. Well, I could get that and just times it by -3 or yeah, but it's easier to get rid of -3 from 1, right? So let's just do that. I'll tell you why we are doing that, right? We're trying to get rid of this. What are you doing, right? Well, if we eliminate this, right? Now this is the only leading coefficient and this becomes 0. So all I have to do is just flip it again. And once I flip it, it's 6, right? I know in the solution they type the 6 out. I don't really see why. I have the lower triangle already established. So all I have to do is just -1 times -1, right? Which will be nothing, right? 1 times 1 times 1 times 6, done. Now, if I took out 6, it wouldn't make any difference. So it will be just 6 here, and there will be 1. So that's the number 1 rule, right? So if that's the case, then it's going to be -1 times -1 times 6 times 1, 1, 1, 1. So this will just be 1. Still gives me 6 either way, right? So I don't know why this is necessary to keep doing that. I mean, it's not wrong, but why, right? So, anywho, that wraps it up, 2.2. This is not supposed to be a hard section. We will move to 2.3. So, we'll see you soon.